Okay, so let's take it from when we left yesterday, just a big backpedaling to remember where we were. So, so we recast this in the form of advection by a mean and eddy, and so the total here is the residual. That's the same as the thickness weighted average. And if we neglect the diffusion term, then we have conservation of mean buoyancy following the residual stream flow. Of course, that cannot be true. So here's a cross-section showing the isopycnals and the stream function, the contours. And that can't really go on all the way to the surface, because eventually in this diabatic region, the surface diabatic layer, the streamlines will cross the buoyancy surface, and so the right-hand side will become important. So I'm not sure if I remember to say this yesterday, but this dynamics really holds below the mixed layer and Ekman layer. And then we parameterized the eddy flux according to GM. So the stream function is proportional to the isopycnal slope. And that immediately tells us the slope of the isopycnals is proportional to the wind, rather minus the Ekman transport divided by the eddy coefficient. And if you know the surface buoyancies, or the surface or the buoyancy at the bottom of the mixed layer, then you can solve this this equation quite simply. You can solve it in buoyancy coordinate, or you can solve it in Cartesian coordinate, and you find that the buoyancy is a function of this expression for constant kappa. You know that function at z equals 0, and so using that relation you can then, this is just using characteristics, and you can find the buoyancy at every depth and longitude. And you can work out examples for specified surface buoyancy and specified wind stress. Okay. So now, so far we've talked, so this example illustrates how the stratification is set in the ACC, assuming that there is no residual circulation. But the overturning circulation is the residual circulation. So now we have to look for a solution where this is not 0 by connecting connecting the ACC to the rest of the global ocean. Okay. And so I'm going to run this movie briefly. Oh my God, it's so slow. So this made by NASA, so it must be good. Probably cost $1 million to make it. And so it's an impression of how the overturning works, and you know, it's very impressionistic, but I thought it was cool actually. I liked it. Looks like fish. Very smooth fish flowing around. So that was the North Atlantic. The water sinks, of course, and then it goes back, and I think what is nice is that it shows that it goes all around the world in the return branch. And there you go, South Atlantic. And now it enters the ACC, and it just flows all around the world. And you see some of it goes in the Pacific, some of it goes even in the Indian Ocean, and then it has to do all this big return, this whirl around the world at depth. And you see all the while it's going around. And this part, I think it's well captured. So let me just stop it. But so that's what we have to explain. I mean, so you see this, it's going all around. Okay, and upwelling. So the point is that the dynamics, yes.
Can you make a comment on the timescales? Because at least me, I was very confused. I thought this was the same as the Gulf Stream before I came to Scripps.
I see.
So
Okay. Um, okay. So, yeah. Right. It's not. But you know what is confusing? It's that it's almost in the same place. And I don't have a good figure for that. And I'm not very good at drawing. But, um, so if this is the North Atlantic, so here you have the wind-driven gyres, and here you have the Gulf Stream, right? Now, if you took, so what happens is that, so here is South Africa, let's make it a little bit shorter. So the water comes in here, and some of it comes through here. And then as soon as you leave the channel, if there were no gyres, it would all flow through in the deep water, or intermediate rather water, would flow through in a western boundary current. But now we have gyres as well. And so this western boundary current, actually I have a figure, I'll show it now. No, because Stommel, he knew this back in 1957. Oh, come on. It's like next to the last figure. There it is. So this is Stommel's view of the circulation, and it's actually right in many. So this is the ACC region, water up wells. Of course, there's contribution from the Indo-Pacific, but he's ignoring that for the moment. And then it turns into a western boundary current, and then it reaches the North Atlantic, sinks, and then comes back in a western boundary current at a different level. But you also have gyres that are driven at a shallower level by the pattern of Ekman pumping and suction. And the Gulf Stream would be here, okay, which is not far from there. And the sum of these two patterns gives you something that snakes around. And so what we call the North Atlantic current is this part of the circulation that has been modified by this part. And unlike the Gulf Stream, which in some sense recirculates around the gyre, this current here proceeds through. So you can sort of think of the Gulf Stream as being, I mean, in a very, very simplified way. You can think of the Gulf Stream as that part of the western boundary current that then recirculates around the gyre, and the North Atlantic current as that part that still goes around the gyre but then proceeds north and sinks.
Why is the interhemispheric northern circulation also western intensified?
How else would it cross the equator and conserve PV? It couldn't, right? You can't cross the equator. Someone asked that question the other day.
So for bilateral friction.
Well, or whatever, something that is not PV conserving. So if it crosses the equator, then it cannot conserve PV, and that in the ocean is
so
done
it's the
in the
same
western
as
boundary.
the gyre-like mechanism was western intensified.
Right, yes. That, stirred more about topography and all that.
If we look at the upper panel, while it's true that those two circulation, meaning the overturning and the thermocline cells, might span similar location in space, they're still quite distinct in density space because they're really two separate circulations. You can see them.
Not sure. This part here goes around.
Yeah, some fraction, but the bulk of the transport is not.
No, I agree. Most of them don't, but they're not completely separate. I mean, the circulation is three-dimensional, so when we squash these things, which, we have all these sheets of paper or screens, we have to put them in two-dimension, and it's very difficult to capture the three-dimensional aspect. Oh my God. And not. Yeah. The whole world, yes, probably of the order of 1,000 years. 1,000, yes, something like that. It's long. It's the ocean doesn't move very quickly, with very fast parts and very slow parts. But I think overall it's the order of 1,000. So why do we care about the overturning circulation? And the main reason I think we care is because the heat transport in the ocean, which is this black line, is less towards the ocean, as the atmosphere, tends to transport heat poleward. However, there's a substantial asymmetry in the ocean between the southern hemisphere and the northern hemisphere. There's more heat transport towards the north in the northern hemisphere than there is to the south in the southern hemisphere. And the reason why, and that actually has consequences. If you look at temperatures in the South Atlantic relative to the North Atlantic at equal locations and same side of the boundaries, they're typically 1 degree, sometimes even 4 degrees colder in the southern hemisphere than they are in the northern hemisphere. And that is because the Atlantic transports heat northward everywhere, including the southern hemisphere, which means that it's actually transporting heat towards the equator in the southern hemisphere. And that leads to a net transport which is not symmetric around the equator, which is then compensated by the atmosphere. And that is really the reason, for example, why the ITCZ, intertropical convergence zone, in the atmosphere is shifted away from the equator. Okay. So it's important, even though it's only, maybe 1 petawatt, because it's a relative small basin, and it's partially compensated by the Pacific. But the net result is there is this asymmetry which has global consequences. So that's what we're going to focus on, this interhemispheric cell, primarily in the Atlantic, which transport heat everywhere northward. So the first approach from the theoretical or conceptual point of view is to think about one basin only. It's not true. We have the Indo-Pacific as well, but for the moment. And this is a schematic of what goes on in the Atlantic. Again, zonally average, so as a function of depth and latitude. So here you have this periodic portion of the Southern Ocean that we just determined the stratification of, which is a competition between the overturning on the wind and the eddies that tend to re-stratify. And they come to some agreement which makes these isopycnals very steep. And I'll show you in a second that the fact that they're so steep is due to the absence of boundaries, because you have this big Deacon cell, the Ekman-driven cell, that goes all the way to the bottom and tends to overturn isopycnals. And the eddies, the little vortices of the Southern Ocean, they re-stratified somewhat, but not too much. So those density surfaces here in this periodic region are rather steep. And then there are 2 types of isopycnals. Those here depicted, actually 3 types, in sort of darker blue, that do not come back up again to the surface in the northern hemisphere. Okay, because here it's colder. Okay, there's contribution from salt, which we'll get to, but anyway, denser. So these are the densest water at the surface, and they're not found in the northern hemisphere. So these isopycnals just hit the wall. Now, of course, if you have this situation, you cannot have an adiabatic circulation, that is a circulation that follows isopycnals, because then you would hit the wall and it would have to be 0. So necessarily, any circulation that occurs in this isopycnal range, and remember that we have to think isopycnally, that's a natural vertical coordinate for the ocean. it would have to be diffusive. It would have to cross isopickles. Right? Is that clear?
So what is the overall transport associated to this bottom cell?
18 Sverdrup, is it? 12, 10? I'm not sure. Yeah. Okay. Now then there's, then there are these.
So
Yeah.
we were not seeing this on the NASA movie, right?
No. No. The movie was concerned about this. Yes, that's correct.
So I have another naive question. I mean, here the flux of energy is towards the north hemisphere. No, it's
Okay,
the
so
other way around.
This one,
Yes, yes.
okay, yeah. So this one would, first of all, it doesn't cross the equator very much, and also the isopickle range at depth is very small. So the difference in heat, if you will, between this branch and this branch is very small. So as far as heat transport is concerned, it's very little. It almost carries nothing. Okay, remember when I was showing this picture, you had to change the contour interval, otherwise there wouldn't be anything. So there's very little stratification here. Then there are these isopickles here which do not enter. They're not found in the periodic. Yes.
Why is the Antarctic waters colder or denser than the Arctic waters?
You know, because there is an overturning, and so, so the reason why the Arctic waters are warmer partially is because there is an overturning which transports heat there. So it's a positive, or maybe rather a negative feedback for this cell, but positive one for this, because in fact it's saltier here. So you'd think it'd be denser, but once the circulation gets going, it transports heat northward, and and warms it up. So then there are these isopickles that don't appear in the periodic region of the channel at all, so they're kind of shallow, and that's part of the wind-driven circulation. You know, they reach about 500 meters. Well, not at the equator, but in the subtropics. And then there are these light blue isopickles that exist both in this periodic region and in the northern hemisphere at the surface, and it is along those that you can have an adiabatic circulation in the interior. Of course, near the surface, you always cross the the isopickles. The circulation crosses the isopickles. And of course, this diffusive circulation exists here as well, and I didn't draw the other one here, so it adds to this and subtracts on this side a little bit, so it's not as symmetric as I've drawn it. And did I go forward? Yes. So then this is, in order to have such an adiabatic circulation, it is essential that you have shared isopickles here and here. And so to test this, and then if you lack this sharing of isopickles, then you won't have a strong intermediate and deep circulation. So mid-depth, let's call it mid-depth circulation. So we tested this idea with Christopher Wolf. And again, we went back to our favorite notched shoebox. But this time we started, though, with a high-resolution moderately high resolution, and a somewhat smaller basin than the Atlantic, which is really half as deep, half as long, and half as wide. I'm really glad we did that, because that's 8 times less computation, and this took a very long time, because we did many computations and they were all equilibrated, so each took months to do. And we didn't have salt, just temperature. So buoyancy is proportional to temperature, fairly weak diffusion. And then at the surface, the model is forced by wind stress with easterlies, westerlies in mid and high latitude and easterlies in the tropical region, and a pattern of temperature that the model is relaxed to on a fairly fast time scale. And yeah.
I actually have a question about the previous figure.
Yep.
So the return flow at the surface is actually through the mixed layer?
Yes. No. The return, I'm not sure what you mean by return.
Well, the one that's at the surface that's crossing the
Yes,
isopycnals.
that's right. Yes. Yes, it is.
Does that affect the mixing of the mixed layer for that region? Because then you have a temperature gradient at the surface, horizontal gradient, for instance, in the southern hemisphere.
Yes. Well, near the surface here, it is in competition with the direct wind-driven flow and the Ekman transport, which is really strong. So I think it doesn't make too much difference when you compare to those other flows that are rather faster. So I don't think so. But sure, it contributes to the surface velocity, pressure, and so forth. So anyway, so what are the results? So here, just to show you that there's a lot going on, and all I'm going to show you is time average, zonally average figures. How sad! I mean, given the richness. I mean, really, look at this. I mean, here you have tropical waves with secondary instability on tropical waves. I mean, the works. It's very interesting, but we only have 24 hours in a day. So, as advertised, we did many experiments, and so here is the result of 3 experiments. The first one is one where you don't have a channel, and here it is. Here is the buoyancy zonally and time average field that you get. Amazing. It's all practically all uniform. Yes. No, we use 2 types. One that we and I will get to that. One that we called cold pole, and the other one that we call warm pole. I'm going to talk about them in a second. It doesn't much matter which one you use for this. But what I think, when I told you that the ACC is essential for the stratification and the circulation of the deep and abyssal ocean, here's the proof, and I'll show you the circulation in the next slide. But here's the stratification. You remove the periodic channel, you close it up. This is what you get in the deep, mid-depth, and abyss. Nothing. Okay, and I told you why. Because the Ekman transport in the periodic region is returned at the bottom, so it tends to overturn those isopycnals very, very well. And the eddies, they do what they can to restratify, but they can't do very much. Here, what you have instead of eddies, you have gyres, and you can establish a pressure difference between the eastern and western boundary, and the gyres are very good at restratifying. Think of them as gigantic eddies, or as Stommel used to say, Edwards. So the return of the Ekman transport when you have gyres occurs here at this height instead of down at the bottom. So you have very shallow cells. Yeah.
Do you expect a continuous transition from the case above to the case below when you take a drag passage with a height?
So you're saying if I put a notch here and then I keep?
Yes.
No, actually I don't. I expect a discrete transition at the depth at which. So for example, in this situation, right? Let's look at this. If you put a ridge that is this high, it practically doesn't make much difference, right? Now, but when you start, because there's very little, the slopes here have essentially hit this edge. But if the topography goes above that, then it starts to make a difference. So yes, I don't think it is continuous actually up to a certain threshold or down to a certain threshold. Now the second case, we open up the channel and we have stratification, nice. However, in this case, because the lowest density in the northern hemisphere is higher than the lowest density that you have in the channel, there are no shared isopycnals between the two hemispheres. So there's none of these isopycnals that go that span both hemispheres. All the isopycnals that are in the channel are in this category. Okay. Yeah.
I noticed that you don't use salt. So is it a second order?
No, it's not. It just saves some computer time by not having to solve an extra equation. So
Is that the measured surface temperature or is the temperature you restore to at the surface?
that's right, but we restored at a very fast rate. I don't remember, it was like a week or 10 days. It's very fast. So the surface buoyancy is very strongly clamped to the value.
But don't you have a very deep mixed layer at the surface? So even though if you're restoring timescale, it gets communicated down. So it's probably pretty
No,
simple.
actually, we didn't even have a mixed layer in this calculation.
Well, but you have convection.
Sure. But if you look at, I mean, the surface, at least the zonally average one, is very closely clamped to the values. And you know, the thing about salt is that the boundary condition for salt is one of approximately not of fixed value, but of fixed flux. So you don't know the value, so it's very different. So here we really wanted to test this idea that I showed you before. So we needed to know what the surface buoyancy was. So salt makes a huge difference. And so at least you get stratification, but in fact, as I will show you in the next slide, you don't get much circulation, and I'll show you in a second. And so there is a difference here, and the fact that you have this very shallow homogeneous region, which you also had here, is an indication that there's actually no deep convection going on here, and there's not much of a overturning. So here in fact is the residual overturning, and this is for this case the closed box, the warm pole, and the cold pole. So this is really the gyral circulation that you see here. These are these overturning cells that are very shallow in depth. And it's only in this case where you have shared isopycnals that you develop an interhemispheric overturning. Now, it's not going across the hemisphere very much because this was fairly diffusive calculation. As I said, the diffusivity was 5 × 10⁻⁵. But if you increase the wind, for example, in the Southern Ocean and make it more realistic, because the other calculation had a symmetric wind, westerlies in both hemispheres of the same strength, easterlies in the tropics of the same strength. But if you actually do a more realistic calculation where the wind stress in the Southern Ocean is closer to, you know, the roaring 40s and so forth, then you get a very strong circulation. And also this shows you that the driving is in the Southern Ocean. Okay, you increase the winds in the Southern Ocean, and the circulation that seems to be stemming from the Northern Hemisphere, in fact, it's going all around like that, right? Increases. It doesn't double, but it gets stronger and more interhemispheric. The stratification here, notice that is not, remember our formula for the slope? Probably not, but we, with Genta-McWilliams, we calculated the slope, and that was proportional to the wind divided by the eddy diffusivity. So you'd think if you double the wind, the slope should double. It quite doesn't do that when you really resolve eddies, because that eddy diffusivity obviously depends on the mean state. So obviously a constant diffusivity, no matter what the external parameters are, is wrong. Okay, so that's why we use an eddy resolving model at great pain, effort, and warming of the climate, since those computers heat up like crazy. All right, so that was quite illuminating, I thought, but then, you know, it's really very difficult to do those computations. So can we sort of go back to low resolution models, and how do they do, and so then we compare this to computations which, instead of having 5 kilometers resolution, had 80 kilometers resolution, but also, for reasons that I don't remember anymore, we had a mixed layer. I'm sure they were computational. And then no explicit vertical diffusion, but of course the model is diffusive. The advection scheme is diffusive. And then we chose this eddy. We used Jensen-McWilliams with a constant eddy diffusivity of 500 meter per second, which seemed to sort of, for this set of parameters, work the best. So it's tuned, if you will. And then here's the comparison. This is when the box is closed, and without this explicit diffusivity here is really homogeneous. I mean, disgustingly so. And this is also to show you that this cell that we saw here before was really driven by diffusion. And once you reduce the diffusion, that's really gone, much reduced. And here's is where you have a channel, but the temperature or buoyancy in the northern hemisphere is quite high, and so there's no shared buoyancy between the two regions. And again, this is less diffusive in the vertical, and so this cell disappears, and you have a stratification that is not too much different from the other case, because the in fact there is yes, you could say that in some sense that's, well, I don't know if there's more or less stratification, but anyway, it's similar because the channel can have that steep slope of isopycnals, but the residual circulation is very small. So that solution that we calculated before for zero residual circulation applies very well in this case. Whereas here, when there is a connection in isopycnal space between the two endpoints of the hemispheres, there is a non-zero residual circulation, which changes the stratification a little bit in the channel as well, and of course gives rise to an overturning. And that's true also in the coarse resolution calculation. So now,
Excuse
yes.
me. Can we have ACC without any wind?
Beg your pardon?
Can we have ACC without any wind?
ACC what? Resulting?
Without wind?
Ah, no.
No, not at all.
No. This well, we'll talk about this again. So you're saying if you let me make sure I understand your question. What happens if I turn off the winds in Antarctica? Well, so here we double them and the circulation strengthen. Now if we reduce them, this circulation would weaken until it goes away. So, but let me just show you, because this is what we're going to talk about, is the theory of the general circulation, including the basin. So we've calculated the stratification in the channel, assuming zero residual circulation before, and now we're going to assume non-zero residual circulation. But in order to know what that residual circulation is, we have to connect it to the other end of the world. Okay, and so this is a simple model that does that. So again, we start in the channel because that's where it is important. So the geometry here is, again, we consider a zonally average circulation. We'll get to non-zonal average eventually. Eventually, maybe. As a function of depth and latitude. And there's a periodic region which stops here at y equal to 0. And so the channel ends at y equal minus L sub s. And then there is a region here at y between y equal L and y equal L plus Ln, where eventually convection is occurring. And so in the circumpolar channel, you can assume that approximately the dynamics is the same as before. That is quasi-adiabatic, so the residual circulation transport, the advection by the residual circulation of the mean buoyancy is approximately 0. And that means where, again, I repeat the definitions of the mean and eddy stream function, again using Gent and McWilliam prescription. And the solution, and then for boundary condition, now you have that you know the surface buoyancy at z equals 0. And then the other boundary condition is that you have to patch at y equal to 0 with the solution on the other side in the basin. Okay, so you have to say. So now we're not going to assume that the residual circulation is 0, but we take the general solution of this equation, Jacobian, of psi and b equals 0. It means that psi is a function of b, and that functional relationship is determined by patching with the solution in the. So I think I'm going to skip this because maybe Ralph will talk about it or not. You're going to talk about this? Okay, whatever. It's fine. It's fine. So now, so the assumption. So this is Ralph's home. Ralph will solve this homework. Now we're going to do this homework here, and so the assumption here is that so in the channel you have this sloping solution that we don't know yet because it's not 0. The residual circulation is not 0. And here we will assume that approximately up to this point, y equal L, the isopycnals as drawn here in these blue lines are flat. So they are independent of y. They depend only on z. Okay. So in this region, we have that that original equation, Jacobian, let me write it here. Jacobian of psi bar plus psi star of b bar is equal to kappa b z z bar. And if it's adiabatic, then this is approximately 0. Although here I kept the whole thing. So now, because b bar is not a function of y, but only a function of z in this region here as drawn, you can integrate this in y from this point, or anywhere really, but we integrate it from this point to this point to find that psi at psi plus psi star, the residual circulation, I should have given it a name, at y equal to 0 is equal to psi plus psi star at y equal L plus the integral, which in this case is just a multiplication by this length, since it's independent of y, of the diapycnal term. Now, in the convective region, we make the exactly opposite assumption that B bar is only a function of y and not a function of z. Okay, so these are completely vertical, and because we know them at the surface, that means we know them everywhere. That's very important. And so that, because of thermal wind balance, will generate an east-west flow as drawn here out of the screen at the surface and into the screen at depth. And then when that, and here it is, it's this expression because this is independent of z. And it is a purely baroclinic flow. So what goes in has to come out. So its integral in the vertical has to be 0. That's why even from just thermal wind relationship, you know the whole part. You even know the barotropic part because you assume that its integral is 0. And then you say, well, all that flow, coming out and going in, arrives at the western boundary, and there it turns at 90 degrees and turns into the western boundary current that represents the overturning. And so, and there, because
Sorry.
this...
I understand that the circulation is purely baroclinic, but how do you know H? I mean, it could be confined.
Yeah, exactly. H is determined as part of the solution. Yes, H is a constant, but is yet unknown. It's part of the solution. Yeah, it is. And so, and here, now we're in this region of, in the basin. So the eddies, this parametrization here that is really made for baroclinic eddies is not important. The eddies here are not important. It's not like the ACC, right? Here we have the gyres and all this machinery of saying this flow turns at the western boundary. I mean, that's what a gyre does. And so at the end of the day, you know then the transport here as a function of this delta B, which is the range of isopycnal shared with the Southern Ocean. So that's known. And so now, neglecting this term, neglecting the diabatic term, you know, and neglecting, well, they really are not important, so that's a very good approximation. These terms are 0, so now you know psi bar at y equal L, and so you have the matching condition with all parameters known except H. So here's H is unknown, and it will be determined as part of the solution by requiring that the northernmost value of B here is at depth H. Okay. So that's how it works. So when you do the patching here, so here it is. So here's the equation. Now, psi bar, the residual circulation is a function of the buoyancy. So, and if you use Gentile-McWilliams, you write this in buoyancy coordinate. And you can actually integrate this because now you're in buoyancy coordinates. So z is a function of y and b bar. You know this, the wind, that's a function of y known. You know f, the Coriolis parameter, that's a function of y known. And this you don't know, but fortunately it's only a function of b, so you can integrate this. And so there it is, the solution. And you integrate up to a value of y, which is a function of b bar. And what is this thing? I mean, what is ys of b bar? Well, it's just the inverse of the surface boundary condition. Okay, so you know that Bs, the boundary condition at the surface, is so B bar at z equals 0 is Bs of y. Say, I don't know, sine pi y over some length. So y of b at the surface is the arc sine, well, pi y over L is the arc sine of b s at the surface. So this is ys, which is a function of b at the surface. Okay? So it's known. Something funny happened to this. Hold on. Well. Okay. So now, so how do you find now? So we have everything here except f of, sorry, I'm missing a b bar here. And now we do the patch at y equal to 0. We use this expression that we know. And so here it is. It's a function of z. You substitute it in at y equal to 0, and you have everything in terms of z. Okay, so you substitute this in here. This is known. And so this is a function of, what you get is z as a function of b at y equal to 0. That's the same as knowing the stratification. That is the same as b as a function of z. But as you see, it's all done much more naturally in buoyancy coordinate rather than z coordinates. And we can do the, I mean, so what this boils down is to solving a quadratic equation of z in terms of this known function of b. Okay. So for example, if I had this expression for the surface velocity, ys is a function, is arc sine of b, but you see it doesn't depend on z, so it's known. This is known. This is whatever integral it is, function of b, and then you plug this in here, and you get an equation for z as a function of b, a quadratic equation. Is it clear? Good. Right, and then h. So we need to know h. So at h, that's where our last shared isopycnal is. So that corresponds to the 0 of the overturning stream function, which is f of b. So you set that to 0 and z equal to h. And so that's the expression for h. And it depends on the integral of the wind stress over this range of isopycnals. And of course the diffusivity of the eddies in the channel. So that actually is the same answer that we found for zero residual circulation, because in fact we're calculating the slope at the zero residual circulation point. That's why I thought it was useful to do that first. Okay, yeah.
I am confused by the vertical isopycnal.
Yes.
Because we learned that the convection was localized in small patches. And so if we average, it should have a slope, no? How should we see those vertical?
Yeah, this is supposed to be exactly the convecting region. But you're right, that is never really, that is always re-stratified, and so there is a slope, and this is just an approximation. And so tell you what difference that makes. So you see there's finally you find the maximum of the stream function, which is f, is at h on 2, and you get, delta bh squared divided by 8. And this is always the same. So if you assume that instead of being vertical, they have a slope, instead of this 8, you would get a different number. But as Bill says, this is oceanography. This is only oceanography. So, 8, 2 over 15, what's that among friends? We're not talking about money right here. So where I give you $8, you give me 2, not too good. Okay, so now First of all, let me just say that this looks very easy because we essentially know the surface buoyancy. That helps tremendously. If you change to a condition which would be appropriate for salt for fixed flux, it's hell. Can't do. At least I can't do it yet. Haven't tried very hard, but it's very difficult. Also because when you have fixed flux, you have to have actually diapicnal mixing, because if you have some flux coming in on both sides, it has to get out somewhere in the middle, right? So it's very difficult to do a purely adiabatic calculation and use flux conditions. Yes, but you don't know where the isopickles are, so who knows whether well, it would have to be like that, obviously. Yeah.
Can I ask just, this is a very small clarification for people who know what I'm talking about, but so the first part of the argument with Nicorational and Wallis, the constraint on H is not, right? Do I understand it correctly? Do they discuss what sets H in Nicorational and Wallis? I just don't remember, I'm asking.
I don't know, I can't remember either. I just did it. Maybe it's wrong. Hope not. Okay, you know, as I was, I prepared this also for my class at Scripps this year, so I did the algebra and that's what I got. Hopefully it's right. Right, I'm gonna skip this. Okay, so now, so Nicorational and Wallis have all these sort of specific approximations. You know, the isopickles are straight here and then vertical there, and you know, it's all a little bit contrived, but on the other hand, it leads to a sort of simple solution. But at the end of the day, there's one part that is missing, and that is the diffusion, which in fact contributes or adds to the residual circulation. And when you put diffusivity in, it becomes quite difficult, and you have to solve it numerically. However, you can do scale analysis on the original equations, and what you find is this balance, which actually was done many years before by this very influential paper. And I would like you to present it to you, because I think it's a very insightful way of looking at the problem, and also it's helpful when you want to extend these conceptual models through 3 dimensions. So in this paper, Canadesican considered the circulation above a generic isopycnal in the mid-depth range, the one where the mid-depth overturning is going on. And of course, this isopycnal must surface, outcrop, both in the periodic region of the Southern Ocean and in the northern hemisphere of the basin. And again, he was considering just one basin. And then he just does the buoyancy budget. What goes in and what comes out. So what comes in here is the Ekman transport. And it doesn't come out because, as we remember, the Ekman transport is returned way below this isopycnal. Then there's eddy fluxes that try to restratify, so they have the opposite sign. So in some sense, we can consider them as buoyancy getting out of that isopycnal. Then there is, of course, diffusive upwelling a la Stommel Monk idea, which, okay, Raf will show you that that's not how it works, but it's considered to happen in a diffusive way, spread over the whole area. And then all of this stuff coming in has to get out, right? And it gets out through the sinking, and that's the convection happening out of that isopycnal. So that's the budget. It's just, you know, very simple physics. Problem is then you have to associate all these to all these processes a form which depends on one unknown, which is the depth of this isopycnal. And this is for a generic isopycnal, but really what it represents is that bounding isopycnal that we were considering before. In fact, because in fact it's not true. What it represents in my mind is the I'm just trying to look at values here. Picture. It represents the isopycnal that captures the maximum, right? Maximum sinking. That's how I like to think about it. Okay. So, okay, Ekman transport, that we know. That's not difficult. Now here, if we use Gentile-McWilliams, it should be proportional to the slope of the isopycnal. And so, of course, that's variable in principle, but we approximate with the fact that the slope is linear within the channel, and so that is, as scaling goes, it's just proportional to the depth of the isopycnal divided by the width of the channel. You can perfect that, and it can be done, but it doesn't make too much difference. Now, if it's true that the diffusive, the diabatic term is diffuse, then that's proportional to the diffusivity times the area divided by the height. And then this velocity here is presumably in geostrophic balance, and so it's proportional to the difference between the height, the difference of the squares of the height of on the eastern side minus the height of the western side times the density difference and divided by f. And this too is kind of arbitrary, but there you go. Now, really what should occur here is the difference between the square of the height on the east minus the square on the height of the west. This is just geostrophy. Okay, geostrophy and hydrostatic balance. And then, depending on what shape exactly it has, there's some numerical factor here. In Vallis, that factor, if the isopycnals are completely straight, is 1/4. Otherwise, it's some other number, but it's sort of a number of order 1. And so, the depth of this isopycnal, and hence the sinking, because this, once you know h, you know the sinking. So in this equation, the unknown is h, and you assume all the other parameters to be known. Okay. And so you can solve for that, and that is essentially the scaling that you get out of the more complex extended model that I showed you before, including diffusion. What is interesting to notice is that adding diffusion makes h bigger and makes the sinking bigger. So diffusion, the diabatic term, increases the amount of sinking, okay, in the northern hemisphere. Now, you can take various limits of this scaling. For example, you can ignore, that's what happens in the closed box that we saw at the beginning in the numerical simulation where there's no channel. These are all processes that occur in the channel. If you don't have these, you just have this balance. That's a diffusive limit. And in that case, the h is proportional to the diffusivity to the 1/3, and so Vallis and Nikorashin in either that paper, the same paper I saw it before, or another one I don't remember. They show, well, I don't know if you think this is a serious scaling, but you know, they have like 3 points. But anyway, this has been verified by many calculations before. So, and in this case, the overturning scales like the diffusivity to the 2/3 power. Now, in the simulations that Christopher and I did, the diffusivity was very small, which is why in those computations with closed, no channels in a completely closed box, our overturning was so weak. So we were sort of in the 10 to the minus 5 range, so it was very small. Now this should be compared, this diffusive limit, with rotation to the non-rotating horizontal convection that Bill talked about in his first lecture. This is called Rossby scaling, and which also depends on the diffusivity. Now in that case there is no rotation, so in the momentum balance, the temperature gradient, instead of being balanced by the Coriolis force through thermal wind balances, they're balanced by viscosity. So here you see there's a dependence on F, whereas here's a dependence on viscosity. And the overturning then goes like the diffusivity to the 4/5. So for fixed Prandtl number where kappa over nu is fixed, it would go like the diffusivity to the 3/5. So different scaling power, but still goes to 0 as the diffusivity goes to 0. Okay. And that's because essentially you take out the mechanical forcing that is given in the channel region. So the opposite limit is the adiabatic limit, where the sinking is balanced by the wind stress in the Southern Ocean and sort of damped by the restratification by the eddies. If you completely ignore these for a moment, then the strength of the circulation is directly proportional to the wind stress in the Southern Ocean. And so here are some numerical simulations to verify this scaling, again performed by Nikorashin and Vallis in this limit. Okay, so I didn't talk about, so I hope I've convinced you that the stratification in both the mid-depth and the abyss is set in the ACC region. And that's because the surface Ekman transport is returned very deep, and so it overturns isopickles until they are restratified by the eddies, but the eddies are not too good. They're not very efficient at that restratification. Having boundaries and the associated gyres is much, much more efficient. And the strength of the rock is essentially a competition in the adiabatic limit between Ekman transport in the Ekman versus eddy transport in the ACC. And of course, simple models with parameterized eddy fluxes I think are helpful conceptually, although not quantitative, because the quantitative results depend on the details of the parameterization. So,
may I ask one thing? Your
yes.
first statement that you have proven that the deep and abyssal stratification is set by the ACC in the ACC region. Is it fair to say that if you go back to Walter Munk insisting that there was a large diffusivity starting from 1,000 meters downward, you would get a stratification also in the abyss? So one hasn't discounted that possibility.
No, you're right, because there is a contribution of the residual overturning, and that the residual overturning depends on what is going on in the interior of the basin. So it is, but so I agree with you. But this just went forward. But yeah, so maybe the abyss. I mean, it's not completely. It's an interplay between the two processes. Now, pardon? Well, hell, we wouldn't want to do that. So as I was preparing this lecture, I thought that it was a little bit curious that the effect of the wind stress in the sinking region didn't play any role at all. And so I offer you an idea which is probably certainly wrong, but there you go, that I just had in the last month. So so the way that these models work is they say, okay, well, the velocity, or actually this is the vertically integrated meridional velocity, the transport is just in geostrophic balance in the upper part of the mid-depth overturning. And so that's how you got that expression for V in terms of the difference. When you zonally average this, or rather zonally integrate this, you get the difference between the pressure or height on the east minus that on the west. But in fact, there is wind stress at the surface in the northern hemisphere as well. And so when you take that vertical integrated transport, you should include it. And so that's my contribution du jour to this field. So let's put it in. So now you calculate the zonally integrated transport, which I don't know why here I decided to call it psi, but anyway, so that's the integral of this with respect to the integral of V divided by F with respect to X, so it's the difference between the east and the west, and then the integral of the Ekman transport in the sinking region. So now that is the new expression for sinking. So now I'm redoing that box model by Canadesican, and the sinking before was this expression, and now I say no, you should take into account this term, which is the return of the Ekman transport in that region. Okay? Because imagine you don't have any overturning circulation, then you still set up a pressure difference between the east and the west, which is there to return the Ekman transport. Because if you have Ekman transport at the surface, you require there is no net transport. You have to have something equal and opposite below, but that's geostrophically balanced, so it sets up a pressure difference between the east and the west. If in addition you have the Mach, well, then that's not zero. Here's the Mach. There's the Mach going through. So here's a modification of the expression for sinking, the new term. Now, if you didn't have these terms, the sinking would be exactly identical as before. But now these terms, the slope of the eddies and the diffusion, the diabatic term, depend on the height. And so when you solve this expression for h, you have to bring this to the other side. It has the opposite sign apparently, but no, because the Coriolis term has the opposite sign, so it kind of adds to this. So you get a deeper region which reduces the overturning. So that was my prediction. Yes? Yes, it's the usual epsilon that depends. Remember that, okay, why is there an epsilon? Because the true expression is the difference between the height at the eastern boundary minus the height at the western boundary. And this h really represents the height at the eastern boundary. Now this is certainly less than this expression is certainly less than the height at the eastern boundary. So there's a factor of, but if you assume that it outcrops on the western boundary, which is sort of the idea in people's mind, then this is zero, but you know, hand waving. So, but regardless of the epsilon, I think the prediction that you get because of these terms, a bigger h and less sinking, is a good prediction, is robust. So I was very lucky because as I was preparing this lecture, there's a student from Oxford visiting Scripps, and she had done this computation changing the wind in the northern hemisphere for her own interest. And so she gave me these pictures, So here, the blue, I hope you people can see the difference between blue and red. Yeah. Most of you, some people can't. I should have done dashed, but sorry. So the blue line is with increased wind. So my prediction is the height of the isopickle will get deeper. True. At least for these two isopickles who are in the middle of the mid-depth region. And then here's the difference in the overturning between the symmetric wind, that would mean large wind, and weak wind. Symmetric minus asymmetric. Symmetric minus asymmetric. So the asymmetric is with weaker wind. So it's larger, it's positive. Sorry? Well, it's the resulting overturning that is the blue line, and it's sort of positive. So now I'm having doubt that it's the anomaly, yes, and it's positive. So it looks like it's actually bigger for the bigger winds, isn't it? Okay. Yes, that's right. So I have to think about that if it agrees with the theory. Now I'm having doubt. Now I'm confused. Anyways, let's press on. Oh, no. I don't want this movie to go on. How do I stop it? Okay. So, well, we've talked about this, so I want to go a little bit on. Now, we've only talked about one basin. But in fact, there are two, or maybe three, but I like to lump the Pacific and the Indian Ocean together because sort of the Indian Ocean is sort of an extension of the Pacific, the way I view it, at least geometrically. And so at least this is how it's done. So here's a circulation zonally averaged. This is in the Southern Ocean. So south of 32 South, there really is no distinction between basins. And so you just see the tail end of the mid-depth circulation, and mostly very prominent, the abyssal cell. Now in the Atlantic sector, you have this very nice mid-depth cell, which is essentially absent in the Pacific. This is just the wind-driven circulation, whereas this abyssal cell is very visible in this Indo-Pacific sector because it's huge. The Indo-Pacific sector is enormous. This is the zonal integral. So it's, much larger because it's a much larger longitude. So now the essential point that we have to understand, not one of the essential points, is, and this is a schematic of the global circulation, is the fact that so water is upwelling all along these longitudes, and you generate these abyssal cell here in the Indian and Pacific Ocean, and then you have water from the Ekman transport, right, entering the Atlantic, entering the Indian Ocean, entering the Pacific, and then it all sinks into the Atlantic. So this water that entered the Indian Ocean and the Pacific is not going to sink in the Pacific, so it has to make its way to the Atlantic in order to sink. And so this is how it does it, primarily. It goes around the tip of South Africa and makes its way to the North Atlantic, and then the loop restarts. So we have to explain what are the consequences of water entering the Indo-Pacific returns to the Atlantic. Well, what I'm going to show you next is that this loop here, like that, is very beneficial for deep water formation in the Atlantic, because as this water makes its tour around the world and finally gets to the Atlantic through this region, it carries a lot of the salt that is in this subtropical region of the Indian Ocean to the Atlantic and makes the Atlantic saltier, enabling convection and enabling densification of the surface water here. Because one of the reasons you might ask yourself is, well, why isn't there a mid-depth overturning in the Pacific? It's very cold. Actually, the temperatures here are colder than in the Atlantic, but it's a lot fresher. And so it is the salt. And why is it that it's saltier in the Atlantic than in the Pacific? So you can generalize that insightful model of canadescent to have now two basins, assume that there's only one sinking, and then add this element of exchange of water, or rather transport of water from this non-sinking Indo-Pacific basin into the Atlantic. Yes.
What's the red curve? Is the Agulhas rings or?
No, well, it doesn't have to be just rings, but it is the transport. Now, when you have two basins, and you have buoyancy input into this region here from both Ekman transport in that sector entering and an upwelling, well, everywhere, right? So you have a net input in this sector of buoyancy, and there's nowhere to go here because this doesn't sink. So the only place where you can get where you flush things out is this region. So you have to have transport of all this stuff entering this sector into the Atlantic, and that is this red curve. And the reason why I painted it red is because in oceanographic jargon it's called the warm route. Because in principle you could go around this place here. That would be called the cold route, but that's not what happens.
Can I have a question?
Yeah.
So this is from the ocean side. I mean, from the atmosphere side, you have the storm track and evaporate near the west boundary current region, and then they're going to precipitate down. So for the Pacific, they can the basin size is big enough so they can precipitate within the same basin. But for the Atlantic, they're not going to.
So in a nutshell, there is an excess of precipitation over evaporation over the Pacific sector compared to the Atlantic sector, right?
Yeah. So that's actually give you the same result for a completely different reason.
Right. No, I'm aware of that. Except that in the Indian Ocean, which in my mind should be lumped with the Pacific, there is an excess of evaporation or precipitation. So if you actually do the budget for the Indo-Pacific, then the excess of evaporation or precipitation in the Atlantic, it's practically gone. Nevertheless, as I am an oceanographer, I will give you an explanation that occurs. And so I'm going to skip all this because there's no time. But anyway, you can do, the plumbing. So the budget, blah, blah, blah. And it's just like canadescent, except there's some geostrophic. Now you have two heights to contend with, two equations in two unknowns. And the coupling is the this is not rocket science, this is oceanography. It's the geostrophic transport, which depends on the difference in pressure between these two basins. So, this is just adding a new exchange term. Never mind that. But, except that this model makes a very important prediction that since the geostrophic transport from the non-sinking basin, the Indo-Pacific to the Atlantic, has to be negative, that predicts, and this connection here is in the southern hemisphere, where the Coriolis term is negative. That makes a prediction, without doing any algebra at all, that the depth of the isopycnals in the mid-depth region in the Pacific should be, the depth should be higher than in the Atlantic. And here are observations. So this is the depth of 3 neutral density surfaces at 3 different locations. The solid is in the Atlantic, the dashed is in the Indian. You can see that because it stops there. And the dot dash is in the Pacific. And in the ACC, they're all the same, 3 minutes, yes. But in the Atlantic, but then once you enter the basin, the Atlantic is systematically shallower. This isopycnal is systematically shallower than in the Indo-Pacific, where they're about the same. So, and so, anyways, the point is we check this prediction with a GCM, you know, because we're sort of not very confident of our theories, and where we put salinity and temperature. And this was, you know, a very simple ocean, just one Atlantic sector, one Indo-Pacific sector, joined by a channel, and then the boundaries. There are just 2 boundaries, one here and the other. So this is on the sphere, but the sphere, instead of being 360 degrees wide, is 210 degrees wide, but it's periodic nevertheless. And so we force this with winds, temperature, and freshwater flux, all independent of longitude, only function of latitude. So the Pacific and the Atlantic receive the same amount of fresh water. And yet, when you look at the surface salinity, which is what is depicted here, the Atlantic is way saltier than the Pacific by about 2 PSU, particular salinity unit, whatever that is, and which is just what is observed. So you don't need the freshwater flux if you have an overturning that sinks in the Pacific and sinks in the Atlantic, and there it is. Here's the overturning. Naturally, spontaneously occurs in the Atlantic, not in the Pacific. This is the usual residual overturning plotted for the 2 sectors, and obviously they are in common south of a certain latitude, so then don't look, I mean, this is just the zonal average of everything. Yeah. Just see what's there, nothing.
If everything is symmetric, why would you expect sinking to happen only in one basin?
So the question is, why does it happen there? So you're saying, in principle, it could happen here and have everything reversed? Is that what you're saying?
Yeah.
Or it could be partitioned.
Yeah. What breaks the symmetry between the 2 oceans? Is it just the geometry?
Yes. The only thing that breaks the symmetry is the geometry, and there are 2 symmetries that are broken. One is the width, because this is a different width, and one is the position of the continents. This has a short continent to the east, this has a long continent to the east. And that is the most important symmetry breaking, and the reason is...
Excuse me. So
yes.
have you tried with to change the position of the of Africa?
Yes.
Yes. Okay.
I have.
Yep.
And that's how I know that the width asymmetry is less important, because when we made these equal, there was still a preference for the narrow basin, but the difference in salinity was quite small. Whereas as soon as you move this up to a certain magical point, which I won't go into, then the difference in salinity becomes enormous. And the reason why that is that we have to have exchange between the non-sinking basin and the sinking basin. And that exchange is proportional to the width and the area, because whatever goes into this basin, well, the Ekman transport is proportional. The total Ekman transport, integrated Ekman transport, is proportional to the width, and the diffusive transport is proportional to the area. So if you have sinking here and not here, you have to have more exchange from the non-sinking to the sinking basis that you would have if this short continent was on the east of the wide basin. And that larger exchange transports more salt. Okay, so so here it is, a visualization of that transport. So there's some stuff that just recirculate around, and some stuff that makes it from the Pacific to the Atlantic. And when you swap them, right now the short continent is here, and there's about half of that exchanged, because the width is half and the area is half. And that transports less salt. And so here is the zonally average salinity in the two basins. Here, when you have sinking in the wide basin, and here's where it matters, right? And there's 0.4 PSU difference. Here's the previous picture where sinking occurred in the narrow basin because this short continent was to the east, and there's this is actually vertically integrated, it's not the surface. But you see there's a much more difference. So that's it. So someone asked the other day why the Atlantic is salted than the Pacific, and that's my explanation. And now, just as questions, and we stop here, I'm going to show you how the journey of a particle from the Indo-Pacific to the Atlantic is kind of slow. But and the color is buoyancy. So it doesn't stay on a buoyancy surface in certain regions. In fact, in the upwelling region of the tropics, it changes density. No. Okay, ready to sink. Ready to sink, almost gone. See here okay. Should have had it sped up. Yeah, it's really slow, isn't it? There you go. Sunk. Now it's sunk. And now it's gonna go back. No, but this is, yeah, this is just, yeah, it's 210 degrees. It's not 360. Yeah, and that's all I have. It didn't go back, through the whole world. Okay, I'm done. Oh, don't even have a summary. I forgot to write the summary.
So, I'm sure there are many questions.
In the early shoebox simulation you showed, you mentioned the inclusion of salt will make significant difference. So what kind of major difference we expect in the overturning circulation?
Well, so the main difference is that the surface buoyancy is not prescribed a priori and it adjusts itself. And what happens is when you add salt, which has a fixed flux condition, so the value of the salinity is not known, is that it tends to, given the pattern that we have on Earth, where you have evaporation in the subtropics and precipitation in the subpolar region, the overturning tends to transport salt from the subtropics to the subpolar region and therefore increase the salinity and thus the density at the surface. And that's a positive feedback that is absent when you prescribe the surface temperature. And so in principle, you know, in systems where you have positive feedback, you can have multiple equilibria and so forth. And so that in the absence of other major symmetry breaking features like the ones induced by geometry, you could have sinking actually in the Pacific. But I think that the reason why it doesn't happen is because these geometrical broken symmetries are so strong that you would have to have a much stronger circulation than what we have to overcome them and have multiple equilibria. But to answer your question, you know, we had the situation where we imposed the temperature in the North Atlantic to be quite warm, and so you couldn't have shared isopycnals. When you do that, but add salt, then the salt advection feedback overcomes the buoyancy difference between the periodic channel ACC region and the Northern Hemisphere and establishes an overturning despite the temperatures, the buoyancy range as given by temperature being outside the shared situation. So there's this positive feedback which has many consequences, including that in principle you can shut off the circulation.
Have you made your last simulation with the two continents with an eddy resolving resolution?
No, not yet.
All right. I was wondering how it could change the salinity transport. You
know, that's a very good question because in these laminar solutions, there's, for example, there's very little exchange of salinity. The salinity that gets trapped in these gyres is only diffusively, through the Gentile-McWilliam mechanism, diffused across. And so these channels, they're called channels when you have open streamlines as opposed to closed streamlines, sorry. So these open streamlines flow is very important. But if you have eddies and time dependence, so these boundaries could migrate more, then the geometry of the salt exchange will change a lot, I would imagine. So, beg your pardon? Yeah, exactly. And so perhaps that would occur also instead with these laminar flows would occur in a different way as well. So, these surprisingly take a long time because they take a long time to equilibrate. So when you start from not the right solution, it takes, 4,000 years to equilibrate. So they're long. So I just not really looking forward to doing them in eddy resolving.
Okay, so thanks a
Thank
lot,
you.
Paola.